This is an electron. It orbits the nucleus of the atom. It just kind of exists as a wave around the atom. But it also still has angular momentum, as if it were orbiting. Okay, that sounds confusing, but not because it's wrong, but because we were never shown the right kind of example to make sense of it all. So in this video, I'm going to try to fix that. I'm going to show you a real physical system where a wave carries angular momentum, so you can actually see what this means. You've seen waves rolling toward the shore. You've also made standing waves on a jump rope as a kid. These two types of waves show up everywhere in physics. And because we can picture them, we feel like we understand them. But there's also a third kind of wave that almost nobody talks about, but it's just as real. It doesn't move forward and it doesn't oscillate in place. Instead, it rotates. And when waves rotate, something strange happens. They can carry angular momentum even though no physical particle is spinning. Now, before we continue, I want to thank Raycon for sponsoring this video and sending me their bone conduction headphones. With Mother's Day coming up, if your mom or wife likes to stay active, these are actually a really great gift. They sit right outside of your ears, and instead of blocking your ear canal, they use bone conduction. So the sound travels through the vibrations in your bones. That means I can listen to music, podcasts, or calls while still hearing what's going on around me because nothing's blocking my ear canal. And not only is this a cool way to transfer sound signals to your brain, but it's so much nicer than regular earphones when I'm just going for a walk or doing experiments or even just cleaning up in the lab. I can stay aware of traffic, people, or equipment around me without sacrificing sound quality. They're also built for everyday use. You can get up to 13 hours of battery life, and they're IP68 waterproof and dustproof. So sweat, rain, and even sand isn't a problem. And the no-bud design stays comfortable and doesn't slip while you move. And the nice thing is that Raycon delivers premium performance without the premium price tag. So their quality rivals the big audio brands, but at about half the cost. Over 3 million people already love Raycon, and they back it with a 30-day happiness guarantee. My wife would love to use these on walks or when she's out on errands. So if you're looking for a great Mother's Day gift or just want to pick up a pair for yourself, go to buyraycon.com/theactionlabbc to get 15% off their bone conduction headphones. And thanks again to Raycon for sponsoring this video. Now let's get back to our experiment. I discovered this physics paper published in 1992 called Rotating Waves. Now in this paper, the author mentions something I never heard of. They mentioned that they were able to create these rotating waves using a child's wading pool. I had never seen this demonstration in all my years of physics, and also I couldn't find any real demonstrations of it online, so I knew I had to try this. The hard part was finding the right pool. I went out and bought a bunch of different sizes of pools. This one was too small, and this one was too big and sloshy, so it damped the waves too much. Then I found this traditional kids pool with the hard sides has been around for ages and it worked the best. Now getting these waves to form is more of an art than science. You kind of have to feel the frequency that happens naturally in the pool. But once you get it, it's amazing. I dyed the water black so you can see it here. At first nothing happens, but then suddenly you see these rotating lobes appear. So these rotating waves are not like a whirlpool or something in the pool. The bulk water is not moving in a circle. You can see the bubbles on here just floating as the waves pass by. But it's the waves themselves that are actually moving in a circle. Now these waves actually carry angular momentum, which means they should be able to make something spin. So if you put something a little bit larger in the pool where the waves can interact with it, you can see that those waves actually make the object spin in a circle, so they transfer angular momentum to it. Surprisingly, this rotating wave is a very good analog for other waves that rotate. For example, most of the time, electrons exist as waves around the nucleus of an atom, until we force them to be particles when we measure their exact location. But for most of their life, they exist as waves. So these water waves follow the exact same mathematical structure as electron waves. In this example here, I had 3 lobes. So that would correlate to an electron in the 4f orbital. And this is what that electron wave function looks like for the 4f electron orbital. It's rotating with 3 lobes, just like our water. So the different colors represent the different phase of the wave. And just like our water wave, it has angular momentum as well. In our water, I could have excited it to have 2 lobes, and that would be a d orbital, like this. And 1 lobe would be a p orbital, like this. And water that isn't spinning would be an s orbital with no angular momentum. But wait a minute, if this is what an f orbital and a d and a p orbital look like, then why, if you look these orbitals up online, do they show orbital shapes that look like this and they aren't spinning? It's not just because they don't want to animate them, it's because of a pesky little rule of nature called the uncertainty principle. The uncertainty principle tells us that certain pairs of properties can't be both precisely defined at the same time. So if I describe the electron as a rotating wave with a definite angular momentum, then it doesn't line up in a specific direction in space. So if I know which way the wave is spinning, then the uncertainty principle tells me that the angle is completely spread out. But if I restrict the area to a certain angle, then the momentum becomes not definite, meaning it's in a superposition of clockwise and counterclockwise. In chemistry, atoms are bonded together in specific ways, so this gives us a preferred direction in space for the orbital. And when the wave lines up in a specific direction like that, the electron is no longer behaving like a single rotating wave. Instead, it becomes a combination of opposite rotations that cancel out, forming a standing pattern in place. That doesn't mean that the wave no longer has angular momentum. It means the electron is behaving like both directions at once, so there's no net rotation. So in chemistry, we get these non-rotating standing waves, even though there still is angular momentum. It's amazing that the nature of the fundamental particles of the universe can be so accurately described using a child's pool. Sometimes in physics, principles can span through all phases of reality, from the quantum to the classical. It's no wonder that Nikola Tesla once said, "If you wish to understand the universe, think of energy, frequency, and vibration." And thanks for watching another episode of the Action Lab, and we'll see you next time.